So I was made aware of in the break here, there's an embarrassing mistake on the slide here. So it has to do with the back-off thing. So we have a back-off counter, and of course when the medium is idle for a slot time, then we count that down, and we pause the back-off when the medium becomes idle. No, when it becomes busy. Okay, so we count down until we reach busy, 0 or busy. If it's 0, then we transmit. If it's busy, we wait until it becomes idle again, and then resume counting down. Okay, thank you. Sorry for that. So back to then security, or the next thing in the course, the final new content. Okay, and this content is actually fairly new in the course also. So it was introduced last year, which means that this material has not been on many exams. So if you somehow use exams to predict what's going to be on new exams, then please be aware of that just because this has only been on 1 or 2 exams in the past, it doesn't mean that it's uninteresting. It's just because it was introduced last year. Okay. And so the learning outcomes is, to talk about the symmetric and asymmetric cryptography, know a little bit about those and what hash functions are, and how these could be used then to provide confidentiality, integrity, and authentication. All of these things we will talk about now. So security is a super important topic, as you know, and it's only increasing in I guess, importance as we get more and more connected. So we only scratched the surface here, so I highly recommend that you take a specific course in this if you're interested in the material. What do we mean by security? Well, today we use security which is computational. So this is by the vast majority of all security solutions which are deployed are based on something called computational security. So what that means is that if we say that something is impossible, maybe it's impossible to decrypt an encrypted message, what we really mean by that is not possible with realistic computational resources. Okay. So for instance, maybe we say that if you have access to all the computing power in the world, then maybe you cannot decode a message if you don't spend 10 years of computing time on that. You know, very few people will find that message so important that they will invest these type of resources. Okay, so security here is not absolute. The security we use today on the internet is breakable, but it's not breakable with feasible resources, really. Okay. Computational security, when I say it's not, it actually relies on the assumption that certain mathematical problems are hard to solve. And maybe you heard of this. If we take 2 prime numbers, large prime numbers with hundreds of digits or thousands of digits, and we multiply them together, we get a number which is 2,000 digits or so forth. If you have a 2,000 digit problem which is the product of 2 primes, it's very difficult to factor that into the primes, in the sense that we know exactly what to do, but it takes forever to do it. Okay, so that's an example of a mathematical problem which is known to be difficult, because people have tried this, since the old Greeks. They tried to do this, but they failed to figure out a good algorithm to do this. Good in the sense that it has, that it doesn't require a lot of computations. When the primes become very large. Okay, now real cryptographic schemes are complicated beasts. So sometimes there are bugs in them, and sometimes there are weaknesses that we didn't think of. So they're constantly being analyzed as for weaknesses. And if a weakness is found, then either we take that solution out of service or we patch that. And I don't know, but last year there was a weakness found in WPA2, which is the security used for Wi-Fi. So if we go back here and look here, we see here security WPA2, which is the recommended way to do things. There are also security solutions in Wi-Fi, which you definitely should not use. Something called WEP. Okay, don't use it. It's bad, right? It's really, really bad. Okay, but people thought that this was pretty good. And last year, it turned out it wasn't pretty good. It had a few weaknesses in it, and it needed to be patched. So that's unfortunately how things are, right? That it seems to be rather difficult to do. It's difficult to do this. Okay, so security. When we think of security, the first thing that pops into mind is a security goal called confidentiality or secrecy, and in the book it's called privacy. Now, privacy today has a meaning of protecting personal information, and that's not if you read the book, privacy is actually secrecy or confidentiality. So what do we mean by that? Well, it means that if I want to transmit the message, I encrypt it, and then I can transmit that over a unsecured network where anybody can read my message, but they're unable to figure out what I said because it's in ciphertext, while the receiver that knows the encryption key can decrypt this and read the message. Okay. So suppose we have a user, Alice, that would like to communicate with Bob, and Alice wants to send this plain text, so it's a message, like see you at the pub tonight, or send me $100, whatever, some message here that Alice would like to keep private. Okay, it should only be able to be read by Bob and not by anybody else. So what Alice does then is to take the plain text and call it M, and then send it through an encryption algorithm that produces C, which is known as a ciphertext. And the ciphertext is a function of the message and a key, K. And this key is a secret that Alice has and is shared with Bob. Okay? So Alice and Bob knows about the key, but nobody else. Okay? This ciphertext is then sent over an insecure network, and inside the insecure network is the evil person Eve. Okay, the eavesdropper, somebody who listens in to the conversation, and Eve would like to decode the plain text from Alice. But Eve should be unable to do that because Eve does not know the key. If Eve knows the key, then we're lost. Okay, so that's the classical setup for secrecy. Okay, so Eve sees the ciphertext. Eve also knows exactly what's going on inside this algorithm. I mean, this could be, the source code could be published, right? It also knows exactly what's going on in the source code of the or the decryption algorithm, right? So neither the encryption nor the decryption algorithm are secrets. The only thing which is secret is the key K. Okay. So this follows something called the Kerckhoffs's principle, which is, this old dude in France, I think, that in 1883 stated this principle in other words, but essentially the message that Kerckhoff wanted to convey is that a crypto system should be secure even if everything about the system except the key is public knowledge. So that's the principle that drives secrecy in the future, or in modern days, I would say. Because if somehow the security relies on that this mechanism for encryption is secret, then that would be bad, because as soon as this is leaked somehow, then the security system is compromised, and then we need to replace the entire system. Okay? So it's not a very good way of doing it. And even if you think this is a secret, maybe it's not a secret because Eve knows about it, right? So the principle for modern security is that the only thing that which is allowed to be secret to the attacker, to Eve, is the key, K. And which means that if Eve figures out the key, all things are lost. Okay. So the problem is then, of course, to generate these keys and distribute those in a secure manner. Any questions? Yes?
Could the keys be like the different high prime numbers that are used? Or?
Yeah, I can talk a little bit what keys are. We can see an example first, and you can get a flavor for what the keys should be like. Yeah.
Are the keys sent every time you send a message as well? Or is it
Pardon me. So
the keys, are they sent once or every time you send a message?
hold that question. So yeah. So one way to do this, which is a very good system from a security point of view, but very, very impractical, is something called a one-time pad. Okay. So this is used, but not very, very often actually. Okay. So one-time pad. What is that? Well, let's assume that M here, the plain text, has n bits in it. 1,000 bits or 2,000 bits or 2 gazillion bits, I don't know, but something. Then this is a very good secure scheme, is that we generate a key k randomly, okay, so random zeros and ones, so random n-bit pattern. Zeros and ones would equal probability, so it's a completely random string, okay, and then this is shared between Alice and Bob somehow. And then the encryption is very, very simple. We take the ciphertext as being M and then XOR with K. So this is modulo 2 addition. So you can think of K here as scrambling the bits in M. For each 1 in K, the corresponding bit in M is flipped. For each 0 in K, the corresponding bit is not flipped. Okay? And it's flipped completely randomly then. Okay. So for Eve that sees C, it looks like a completely random n-bit string. And C has no way of undoing this operation. There is nothing in C that gives a hint on what M is. Okay. And the reason why this is the case is that we select K to be a completely random bit sequence. Okay. The decryption is super simple. We just take C and then we XOR with K. Why does this work? Well, C is M plus K, so it's M plus K plus K. K plus K is 0. M plus 0 is M. Voila. Okay? Very, very, very simple. Right? And completely secure. So why is this not used? Well, it is because the one-time pad is secure if and only if the key is never reused. Okay? So for each new message M, we need a new key. So the problem is that we need a unique secret key, and that needs to be shared between Alice and Bob, just as, okay, which has as many bits as the message that we wanted to transmit. Okay, so how are we going to share the key? Because the key is not the secret thing. Let's see now. The problem was we wanted to send a message securely, and then we used the key. And then to use that, we need to send the key securely. Okay, so this is a problem, right? And then the key must have the same length as the plain text. So back in the days of the Cold War, there was a telephone line or some type of communication scheme between the White House and Moscow, right? And it used a one-time pad. Do you know how they transmitted the key? Through a courier, okay? So they typed out the sequence in paper, put that into like a suitcase, handcuffed that to a courier. I imagine, I don't know this, but the courier took this and took the flight from Washington to Moscow or the other way around, and then delivered the key. So the key was pre-distributed, right? And then when it was time to use it, they used the key, and when they ran out of the key, they had to print out new papers and then go back and forth. Okay, so it sort of works, right? But it's not super practical if you want to buy things at Amazon, right? So we must find a better way for doing this. But these are not useless schemes in general, so we will see how we can actually leverage different techniques to use a variation of this. So the one-time pad is an example of something called symmetric cryptography. And symmetric means that Alice and Bob share the same key, or symmetric is in the sense that we use the same key for encryption as for decryption. Okay, so that's the symmetrical part of it. Okay. An example of a practical scheme for this is this advanced encryption standard called AES, which seems to be a pretty good one so far. It's heavily used in practice. Okay, so can we do better or can we do differently? So we talked about symmetrical keys here, or crypto system, meaning that you use the same key for encryption and decryption. So there is something called asymmetric cryptography where we don't. We have different keys, one for encryption and one for decryption. And this is also known as public key cryptography. And so this was invented in the 70s, I think. That really what makes things work on the internet today. So it was a revolution at the time, and it has profound impact on today's society. So the key idea here is that each user of a network has a secret or a private key, okay, called SK. And coupled to this private key, there is also a public key called PK. Okay, so a user has two keys, a secret key and a public key. These are connected to each other. Encryption is done with the public key, which is known to everyone. Decryption is done with the secret key, which is only known to the person who owns that secret key. Okay, so which means that anyone, you know, Alice, Eve, whoever, who wants to communicate with Bob should use Bob's public key to encrypt the plain text. And then it's implied that only Bob can decrypt the ciphertext, because this decryption uses Bob's private key, and only Bob knows about the private key. Okay, so the following idea is that we have Bob here generates a key pair, one which is the secret part. Bob keeps that for himself. Okay, so it's Bob's secret. But then there is a public key which is connected to this secret key, and Bob basically published this, you know, on a website or wherever, or send it to his friends and whatever, Facebook or whatever, right? So anybody can get hold of the public key, but nobody except Bob knows the secret key. Which means that Alice can encrypt a plain text using the public key. Anybody could do the encryption, because the public key is not a secret. This encryption algorithm is well known. It's, you have the source code for it. And then you get the ciphertext. And the key idea here is that nobody can decrypt the ciphertext except Bob, because decrypting the ciphertext requires the knowledge of the secret key. Okay. Questions? Okay. So asymmetric means that there is a public key for encryption and a secret key for decryption. Okay. It's also known as public key cryptography. Right. Okay. Why is this good? Well, the public key is not a secret, which means that, I said this many times now, anyone can encrypt messages. Okay, and the advantage of this is it could also be people that Bob have never met, right? So Bob here could be, for instance, Amazon. And if you want to communicate with Amazon, you don't want, I mean, you never went to Amazon and got a special key for you, but we know Amazon's public key, so we can communicate with Amazon in a secure way. Only Amazon can decode the message to Amazon. Right? So it's very convenient from that matter. The secret key is a secret, sort of, right? Which means that only Amazon or Bob can decrypt the message. Okay, so we have something which is secure, and we have really facilitated the process of handing out encryption keys, right? Because they're not secret. So we can just post them. Okay. Key distribution is therefore easier, but we will see it's not without problems. Okay. So it's easier than this private key or symmetrical key encryption. We don't need suitcases and couriers and things like this. Okay. The main drawback, what is that? Well, it takes these encryption and decryption algorithms is 100 to 1,000 times more complicated than private key algorithms. Okay, so we need more powerful hardware, software to do the encryption, decryption. And this could be demanding then if there's a lot of traffic, right, that needs to be decrypted and encrypted. So a practical solution to the latter things here is that we use Alice and Bob, if they want to communicate, then they use public key crypto to share a key, a private key that only they know about. It's sometimes known as a session key. And then they use private key crypto, symmetrical crypto, with the session key to communicate large volumes of data until they're done. And once they're done, they throw away the key. Okay? So when I would like to talk to Amazon, for instance, I use Amazon's public key to contact Amazon, and with Amazon to agree upon a secret key that only we know about. And we use that in a symmetrical fashion. It's used for encryption and decryption, because that's 1,000 to 100 times more efficient. When we're done, we throw the keys away. And if I want to communicate again, I go through the same process. Okay? Questions? Okay. No, secrecy is not the only thing we care about. Far from. Okay, we care about something called integrity and authenticity also. This is sometimes connected to each other, so sometimes we bundle these together. But integrity and secrecy are two things which are more or less orthogonal to each other. We can have one but not the other, or the opposite way, or we can have both or none, right? So what is that? What is meant by this? Well, cryptography can be used to provide authenticity. Okay, and the authenticity is that we can verify that a message is from the claimed sender. So if I get a message and it says, okay, this message is from Alice. How do I know that this is from Alice? I just got it in my mailbox. I have no idea, right? So I need to have a method for checking that this message, which has been signed by Alice, is actually signed by Alice and not by somebody else. Okay, so that's authenticity. Integrity is to guarantee that the messages has not been altered in transmission. Okay, so if I get a message from Alice, how do I know that the content of the message has not been tampered with? Right? How do I know that the message is the message that Alice sent? Okay, and that's called integrity. So, for instance, if we want to interact with our bank over the internet, which many people do on a daily basis. So, I mean, first of all, how do I know that the web server that I'm connected to right now is actually the bank and not somebody else? I don't know. I would like to know, but this is to do that we need authenticity. Right? So when I connect to a web server and the web server says, hey, I'm Handelsbanken or Skandiabanken, right? I would like to know that this is actually true. Okay, so that's authenticity. And then if I have authenticity, so I know that I'm connected to the bank server, I would like to know that money transfers or whatever bank thing I do goes to the right destination. That is, it goes to the bank server and has the right amount, say. That the money transfers go to the right person with the right amount. Okay, and this is basically to have integrity. So when I tell my bank to transmit, 200 kronas to my friend, I would like to be exactly 200 kronas, not 2,000 krona, and I would also like it to go to the right friend. Okay. Now, if we have confidentiality, that does not give us either authenticity nor integrity, typically. So, confidentiality does not prevent tampering with the message. Okay, can we see that? For the one-time pad, it's trivial to change bits in the plain text by just flipping the corresponding bits in the ciphertext. Okay. So if this was the bits that we would like to transmit, this is the plain text. And then we have the key, which is 0, 1, 0. Then the ciphertext that we transmit is 1, 1, 1, right? So this is the key, and this is the ciphertext. So if I am an attacker and I would like the receiver to decode the wrong message, I just take the ciphertext 1, 1, 1, and I say, okay, I would like to flip the first bit. Then I flip that first bit and send that to the receiver. And the receiver would decode what? 0, 0, 1. The receiver knows the key, and it will then decode this plain text. Okay, so even though I was unable to detect or decrypt the plain text 101, I had no idea what the plain text is, I can flip bits at will, at any position if I like, right? So this perfect secrecy scheme we had, a one-time pad, has no integrity whatsoever. Okay, so maybe I know that the first bit is, launch a nuclear missile, right? I can flip that if I like. That's clearly not so very good, right? Okay, so the solution to this, there is a private key solution and a secret key or symmetrical key solution to this. The private key, symmetrical key solution to this is to use something called message authentication codes. And so what do? Well, we have the message, and then from the message we send that through a encryption algorithm, this message authentication code, and we produce a tag T. Okay, and the T is specific to the message and the key that we use. And as before, the key is a secret only known to the legitimate receiver. So Bob here has the key. An intruder, Trudy, here, has no knowledge about the key, but is otherwise can observe both the message and the tag, which we transmit in parallel or just after each other. Note that the message itself is not secret here, because that's not the security goal here. We just want to make sure that this message is not altered in transmission. Okay, so what Trudy can do is then look at M and T and try to output the forgery M prime and T prime. Okay, and then the security here, we can guarantee the following security, that the decryption algorithm here, which is called verify, it looks at M prime and T prime and will output a binary bit B, which is equal to 1 if M prime and T prime are legitimate pairs if K is the key. Okay, so B here would be 0 if it's if the receiver thinks it's a forgery, and 1 if it thinks it's okay. So Bob accepts a message M prime if B is equal to 1 and rejects M prime if B is equal to 0. And then one can show that there exist codes here that generates these tags T such that it's practically impossible for Trudy to forge a message. Okay, that is to output an M prime T prime which is not equal to MT. Either M is wrong or T is wrong, such that B is equal to 1. One can actually show this. Okay, I'm not going to go into the details here, but that's actually possible. Okay, so which means that here we have a scheme where forgeries are impossible. Impossible meaning with bounded computational resources, because Trudy with enough computational resources could output an M prime T prime, which is legitimate. Okay. The thing that makes this work is that the tag depends on this secret key. Okay. which means that if b is equal to 1 here, and and Bob knows that Alice is the only person on Earth that has this key k, then Bob can actually know also that this message is not only not tampered with, but it actually also comes from Alice. So we here have a measure of authenticity also, right? But Bob will have another. Bob cannot prove to anybody else that message M came from Alice, and this is sometimes something which is important. So if Bob is the bank and receives a message from Alice to say, okay, transfer all the money to this guy, right? And the bank does that, and later on Alice says, well, I didn't say that. Then Bob cannot prove to a court that the message he received was actually from Alice. Okay? He can only prove that it came from somebody who has the key, and maybe the key was compromised. Okay. The public key solution to this is there is one, and it's something called digital signatures. And basically it's the same idea. The only difference now is that we have two keys, one secret key and one public key. Okay, and this is connected then to Alice. Now there is a tweak to this, where one key is used for signing and one is for checking that the signature is correct. But the order is now a little bit reversed from the secrecy scheme, where we encrypt using the public key and decrypt using the secret key. Here's the other way around. Okay, we do encryption, that is the signature, using the secret key, and decryption using the public key. So Alice generates a pair of keys, one secret key and one public key. The public key is known to everyone. The secret key is only known to Alice. Alice signs the message and gets a signature. And there are methods for doing that, such that Trudy cannot forge a message. Okay. So signing is used using the secret key, and the verification signature is done using the public key. And the advantage of this is that only Alice can sign. Okay. Why is that? Because signing is done with the secret key, and only Alice has it. The good thing is that anybody can check the signature, not only Bob, anyone can check this signature, because the signature checking is based on the public key, which means that a court of law, for instance, can check that this message, comes from somebody who has the access to Alice's secret key. Okay. So Alice cannot deny that she has signed the message, otherwise than say, okay, somebody stole my secret key. That's the only defense. Right? Authenticity is implied here. Again, if this private key belongs to Alice, then we know that a message signed with the secret key that go through the verifying circuitry here can only come from Alice. Questions? Okay. Hash functions. What are those? Okay, I'm going to do this. Let's see, how much time do we have? We have 10 minutes. Okay. Hash functions. So a hash function is something that computes an n-bit string called a digest of x, where x computes a digest x of a message m of arbitrary length. So if h is a hash function, it takes m, an arbitrary number of bits, and produces an x, which is a fixed number of bits. Okay, so x here is n bit, and m here is m bit, where m is arbitrary. We can choose that to be any number. The digest is similar to parity bits for systematic block code, with the difference is that x here, most codes have a fixed input number of bits. The difference here is that it's impossible, that is very hard, to find two messages which has the same hash. Okay, so there are of course two messages which has the same hash, because if we think of this as, you know, suppose m is equal to 4 and n is equal to 2, the hash function takes 4-bit patterns and map that onto 2-bit patterns. There are 16 inputs and 4 possible outputs. So of course there is a number of inputs that produces the same output. This is true. This is true also for any hash function. But the problem is then when we make m and n very large, it becomes increasingly more difficult to find two inputs, two different m's, that produces the same output. It's actually a little bit magical when you think about it, but that is actually the case. So there exist these hash functions for where these collisions, as they are known, are very hard to find. Which means that if we have one of these hash functions which is collision free or collision resistant, then instead of working with m, we can work with x when it comes to signing messages and things like this. And the advantage of this is that these could be relatively few bits, and the computational complexity in signing x compared to m could be much smaller. So we do this for complexity reduction. So there are some hash functions, maybe you've seen them before. There's something called MD5, which we should really not use too much. But if you get a security update from Microsoft or something like that, they are typically signed by an MD5 checksum. There's something called SHA-1 and SHA-2 and SHA-3. These are also, if you heard of these before, these are examples of hash functions. Okay, so what do we use hash functions for? Well, basically we use, if we want to sign a message m, instead of signing m directly, we first compute the hash of m and then sign that. So this is the hash and sign paradigm. And this is used quite often in practice to reduce the complexity, because the complexity lies here, and the complexity scales with the number of input bits here. So, I mean, if this is, for instance, if the message is 1 gigabyte and this is 128 bit, then you can understand that there is a huge difference in computational complexity. Okay. The practical schemes include these. If you've seen them before, maybe you heard of them, maybe not. Okay. Certificates. What are those? So to check a signature for authenticity uses the sender's public key, right? And we know that the public key is something which is posted publicly. But how does Bob really know that a key, say the key PKA, is actually Alice's public key and not the hacker's public key? How do we know that a public key is tied to a person? Okay, because that's crucial for things to work now. So the solution to this is that if there is a person, Charlie, that we trust, okay, suppose I'm Bob, I know Charlie. Charlie's a trustworthy guy, and he knows that Alice's key is PKA. Then Charlie can certify that to me. Charlie can tell me, okay, well, you know, PKA is Alice's key. I trust Charlie, and therefore I can trust that PKA is Alice's key. So Charlie here is a certificate authority, a CA, which is some trusted organization that I trust. Maybe it's there's a bunch of those. You know, VeriSign is one, and GoDaddy is another one. There are organizations which are trustworthy organization that keeps track of public keys. These certificate authorities, they have a well-known public key, okay, and a very, very secret key also. So Charlie can now provide Alice's with a certificate saying certificate C to A, which says this. It's signed with the secret key of Charlie. So SKC is Charlie's secret key. And Charlie says the public key PKA belongs to Alice. Alice can get this message and send that with her own messages. Okay? And then anybody who trusts Charlie can see that Charlie says that Alice's key is PKA. And since I trust Charlie, maybe I never met Alice. I don't know about Alice, but I trust Charlie. So Charlie says that Alice's public key is PKA. And therefore, if Alice sends this certificate to Bob, and Bob has never seen Alice before, but Bob can verify that the certificate has been signed by Charlie, Bob trusts Charlie's and therefore trusts that PKA is Alice's public key. Okay, so that's the purpose of a certificate. A certificate is a statement from a trusted authority that binds public keys to identities. So is now everything okay? No, wait a minute. How does Charlie know that Alice's public key is PKA? Okay. Solution to this is that Alice actually has to go to Charlie with her key and prove her identity. You know. But this is a practical solution to this problem. So if I want to have a certificate of my public key, I actually have to go somewhere and show my ID and show my string of bits, and then the person for this certificate authority needs to check my ID and so forth, and then gives me a certificate back, right? And that's why most of us don't have certified public keys, right? I don't. Does any of you have certified public key? No. Okay. That's why we have BankID and all these other solutions, right? Now, how does Bob know that Charlie's public key is PKC? It's another problem. That's actually hard-coded into the operating systems and web browsers. So when you buy a new computer, the operating system there has hard-coded public keys for a number of certificate authorities that Microsoft or Apple or whatever trusts. Question?
How many of those authorities are there?
Way too many, hundreds. Yeah, so this is a big problem actually, because sometimes these are, maybe not so stable always. So it happens that the private key of a certificate authority is actually hacked, which causes a lot of security concern. So there are many of these certificate authorities, which is a problem. You can go into your web browser, Firefox or whatever, and see how many certificate authorities they trust. Quite a few of them. Yeah. Okay, so I wanted to finish here, so the whole security thing here is super big topic, and I haven't even talked about privacy here. So if I would recommend a course to take or some things to add to your knowledge base, then a little bit of computer security would not be a bad thing to know. Just as a human being living in the age we do, to know what risks you are when you say, okay, when your web browser says this certificate is not valid, what does that really mean, and things like that. Then take one of these network security courses. There are good ones also online at Coursera and whatever. And there are a few links to these on the ping pong page if you want to see real experts talk about this, because this is not my area of expertise per se. All right, that's it for today.